TMUA questions that do things like what must be true and which is necessary. So it gives you a list of options and it's asking which of them must be true. And to do these questions, there's a very straightforward way of doing them most of the time, and that is by choosing counterexamples. You need to read the question carefully, you need to find some counterexamples that make each of the things not true, and therefore they don't always have to be true. So let's go through it. This is the very first one we'll do from 2019 paper 2. Given that AB equals AC, which of the following must be true? So what I need to do is I need to say, okay, this one is saying that A must equal 0. Can I find a counterexample to that? Well, yeah, if both B and C are 0 and A is anything else, then 2 times 0 equals 2 times 0, and A doesn't have to be 0. So we can cross that one off the list. Does B have to equal 0 or C have to equal 0? Well, no, again, because we could just make A 0, and then we can make B and C whatever we want. And then we don't have to make them 0. So that one doesn't have to be true either. And of course, I've already found a counterexample to this case. Here it is. So that doesn't have to be true either. And none of them have to be true. So when we see this language, we are going to go with counterexamples. That is what we are going to do every single time. Next one. Of course, you can pause the video and give each one of these a go before I do them. But here we're looking at an arithmetic sequence that has n terms, all of which are integers. The sum of the series is 20. Doesn't say how many terms or anything like that. Which of the following must be true? The first term is even. Well, just make an arithmetic sequence that starts at an odd number and make it add up to 20. Here's an example. 9, 11, add up to 20, a difference of 2, arithmetic. Good, that doesn't have to be true because it starts with an odd. N is even, that's the number of terms. So can you find us an arithmetic sequence with 1, 3, or 5 terms or so on? Well, I can find one with 1 term, 20. There's a very boring arithmetic sequence with 1 term that sums to 20. So, yeah, no. Common difference is even. Slightly harder to find, but after a little bit of searching, doesn't take too long to find this. Of course, 1 is the obvious difference to go with because that's odd and kind of easy to add these numbers up. These add up to 20. Common difference doesn't have to be even. And so again, none of these are true. So what happens though if you have a condition that is true, that you can't find a counterexample for? Well, you've got a couple of choices. So we'll get to this question here. A less than B less than C less than 0. So okay, we can make a little grid if we want to, and the most obvious thing to try first is maybe this, right? It's the most obvious thing to try. Does that counterexample any of these to start with? Well, AC is positive 3, which is less than AB, which is positive 6, less than A squared, which is 9. So doesn't counterexample this. This one here, B is minus 2 times, this would be minus 4, so that's going to be 8, so that doesn't counterexample that. This one though, minus 1 over minus 2 is a half. Minus 3 over minus 2 is positive 3 over 2, and this is obviously not true, and so it does counterexample that. So that's cool. The very first thing I thought of at least got rid of one of them. Now, it didn't get rid of these two, and you can try some more things, but if you can't find anything, then you've just got to think about it more critically. But the good news is, of course, because you've got rid of this, even if you were to guess from then on, you've got a much better chance. But let's think about these critically then. Well, there's an A running through all of these things. So I could divide everything by A here. Just be careful, A is less than 0. So when I divide everything by A here, I have to flip all the signs. But of course, this here is literally just this written backwards. So this is true, because it's just another version of the original statement. So that's true. This here, well, B is a negative number from here, and so is C plus A. When you add up two negatives, you get a negative. So we've got negative times negative, which is also going to be bigger than 0. So both of these statements are true, and it just takes a little bit of thinking to get that done. But counterexamples first, and then if you can't find any, gotta logically think through the statements a little bit. But always start with counterexamples. So another one here. So again, we can make an A, B, C, D grid here and come up with some numbers. This seems like the most obvious thing to start with. A plus B is 3, which is less than 7, which is good. A plus 3 is 4, which is less than 6. So this holds for both of these statements. A is less than D, so it's not counterable. B is less than C. What if I just swapped around B and C though? Does this hold both of these? Well, A plus B is 4, C plus D is 6, A plus C is 3, B is fine. So that, yeah, that's fine. But B is greater than C here, so this doesn't have to be true. So that fairly obvious counterexample existed that got rid of this one. And again, it's hard to see how you're going to make A bigger than D, right? It's hard to see how you can find a counterexample of this because A is on this side every time. Of course, you can prove that you can't by just adding this to this to get this, I'm just doing 0 plus 0 is 0, this plus this is that, this plus this is that. Take away b and c from everything, from all 3 bits, and you get 2a is less than 2d, so a is less than d. So that one's definitely true. And here again, thinking logically, a plus b is positive because it's bigger than 0, c plus d is positive because it's bigger than 0, so when you add up all 4, or both pairs of positive things, you're going to be bigger than 0. So those two must be true. But again, counterexamples first, then got to think through it a little bit logically. But of course, you can also just guess, right? Once you've got rid of one of them, you've got fewer options to go with, which is better than what you had before. Otherwise, think it through logically if you can. This also applies, oh no, we'll do one more example here, just because we may as well do as many examples as possible. Standard form means that these numbers have to be between 1 and 10. They can be 1, but they can't be 10. That's what standard form is. Counterexamples then. So seems logical if I'm going to counterexample this to make a something like 8.9, and then since I'm going to have to add b to it, I want to make probably b as big as possible. So I may as well make it 9.9. And let's just add these things together. So 8.9 times 10 to the minus 3 is this. 9.9 times 10 to the minus 2 is that. Let's add these together. We get this, 9 plus 0, there with 1 left over, carry over, good, yeah. And that is 1.079 times 10 to the minus 1. And so C is valid, it's above 1. And so this is a valid construction with A, B, and C, these things here. So that's a counterexample then, because A doesn't have to be bigger than 9, so we'll get rid of that. It's also, very efficiently, a counterexample to this and this, because A is bigger than C in my construction, and B is also bigger than C. So it gets rid of those two as well. B bigger than 9, okay, well let's pick A to be as big as possible, so 9.9, B, let's go with 8.9. Add these things together though, and you have a problem, which is that you can't, because you don't have a digit, because this is an 8, and the biggest thing you can throw in as a remainder is 1, because you can't add up two numbers to get 20. This is as big as you can get, and that's 18. Even if you carried a 1 from before, that's only 19. So you can never make this digit, you can never carry 2 into here. This is biggest an 8, because B is biggest 9. So this kind of makes sense that this will never work. We can't quite do this. If you think it through for another 30 seconds, I'm sure you'll figure it out. But we just can't get this to work. We can't make this digit a 10 and put 1 into here, which is what's necessary to make C bigger than 1. So 2 is the only one that's necessary. But again, we got rid of all of those 3 with a very simple counterexample, which essentially, even if you didn't figure that out, your guess would have been between this one and... Oh, in fact, no, you didn't even need to figure this out, did you? Because there's no option for none of them. So as soon as you got rid of these 3, the answer is that. You didn't even have to think this through at all. You could have just underlined this straight away. Interesting, cool. Let's do some more, but this time we're going to be doing graph sketching because it's just as valid to provide counterexamples through sketches. And I've talked about sketching a lot before on this channel, but you can also do counterexample sketches and 2 birds in 1 stone, because I love counterexamples, I love sketches. Let's do both at the same time. So f is a polynomial that has 2 real roots exactly, minus p and p. So it has roots here and here and nowhere else. And the graph that they want you to picture in your mind is this one, which is probably the one that we all thought of immediately. And of course, if you picture this graph in your mind, this first statement, f dashed of x equals 0, so that's has one value. That just means a turning point, doesn't it? F dash is 0 as a turning point for one value. Well, yeah, this graph has a turning point in one place. But again, this isn't the only graph that does this. And we're thinking of counterexamples. Can we think of another graph that does this that doesn't have only one stationary point between the two things? And yeah, think of a quartic graph. You drew those at the start of year 12. That has 3 stationary points, and still only these 2 roots. It's a polynomial, and so this is not necessary, right? It doesn't have to be true. We can find 3 roots instead. Again, if you go back to this graph, that's what they're trying to lead you on with this statement as well, whereby the integral between 0 and between p and minus p is just 2 lots of the integral between p and 0, otherwise saying that this needs to be symmetrical here and here, so these 2 areas are the same. But again, that doesn't have to be true, because you could draw like a cubic like this, where this area is not the same as this one, because this is like convex here, and then this one is, or is this concave here, and this one is convex, sorry. But clearly this area is different to this area. And so you can't just do this. But again, we have 2 roots, so it satisfies this, so this doesn't have to be true either. And then lastly, graph minus f of minus x, it still only has the 2 roots. Now, it's harder to come up with a counterexample to this, so let's think it through very logically. First, what this is asking you to do is flip it in the y-axis, then flip it in the x-axis. It actually doesn't matter which order you do those in. But if you take a graph that has two roots and you flip it in the y-axis, let's just go with first, it's still going to have two roots, right? Because this root just moves over there, this root just moves over there. You don't create any new roots. Like, you can't do that. Then you flip it in the x-axis, but again, when you flip something in the x-axis, the points that stay in the same place are the roots. Everything else flips to the other side. And so you're still only going to have two roots when you flip it in the x-axis. And so this is just by some thinking through what this actually does, you realize that this is definitely always true. But counterexamples got rid of these two. And so even if we couldn't think this through, we'd have been left with a 50-50 shout of this one or this one, which is much better than what you started with before the counterexamples. Let's keep going, because the more of these we do, the better. We've got two cubic functions, and an f of x minus g of x has to be bigger than 0 for all x. Now, what you can think of that as meaning, if you want to sketch some counterexamples, is that means that if you have one cubic, the other cubic has got to be consistently above it, right? So one is always above the other one is what you can think of here. Well, all I can do is I can just draw a random cubic and then just shift it up a few places and call this one f and this one g, and then f minus g is always bigger than 0 because f is always above g. But if I've just taken this cubic and shifted it up, then I've left the a and the p. Those are the same value, because all I did was translate this cubic up a bit. So a does not have to be bigger than p, right? This a and p will be the same value because all I did was shift it up. If you think of it as in terms of a sketch as well, you realize that this just has to be true. Because if you think of this graph as just having to be higher than this one, well, d and s are the y-intercepts, and so d has to be above s. If d is less than s, then there's some point where this graph is below this one, which we're not allowed. So this definitely has to be true. And so just by doing a sketch, and doing the simplest sketch we could think of, we know this is not true, we know this is, and look at all the options that eliminates. We're down to a 1 in 3 guess, which is good, right? That's very good. I think I've underlined this. This ends up being the true one, but that's a bit of spoilers. How do we work out that that's actually true? How do we work out that these are both necessary? In fact, no, we also should have got rid of this one, shouldn't we? Because we know this is true. So it's actually a 1 in 2 guess we got it down to. This one or this one. I've already underlined this because it turns out that's true. But let me just explain why. If you actually do some algebra here instead, if you write f of x minus g of x, which is what I've done here, I guess. What I've done here is a bit confusing. I've said f of x has got to be greater than g of x, which is just this rearranged, and that's f of x, that's g of x. Then I've moved g of x over and factorized all of the x cubed, x squared, x terms like this. I hope that you follow that. Now, the issue here is that this is a cubic, right? This is a cubic graph. And now what do we know about cubics? Well, we know cubics definitely have a root. They definitely start down here and end up here, or start over here and end down here. But either way, cubics are not always positive. They always cross the x-axis somewhere in whatever direction and are always negative somewhere. So what's the only conclusion we can draw from this statement? Well, it's that a equals p, and this isn't even a cubic. A equals p, and this is not a cubic, it's actually a quadratic. Right? And so this also disproves this one as well, because it's actually never the case that a is bigger than p. A has to equal p for this to be true. So now we're down to here, but now we're working with this statement. If b equals q, now if b equals q, then this is of course 0, and we're left with this statement. But again, think of this logically. This is just a line. Something x plus something, mx plus c. This is just a line. But again, lines, just like cubic graphs, definitely have a negative bit and a positive bit, unless the line is just completely flat, in which case the gradient is 0, and so c must equal r, which is what this says. If b equals q, then c equals r. The only way to make this always bigger than 0 is just to make this line a completely flat one above the x-axis, and so c must equal r to get rid of any gradient, and then d must be bigger than s, which is what the statement is. So this one and this one are both true, and the answer is G, as I underlined. I don't think I have any more examples. Oh no, I have one more example. Excellent. Another graph sketching example. Perfect. So here we're looking at, again, we see this language is not which must be true, but which is necessary. It's the same thing. So we have this integral must equal this integral. So in other words, the area between 0 and minus 5 must be the same as the area between 0 and 5. And one interpretation when you look at this that I think lots of people have is, oh, well, this just means that the graph is symmetrical across the y-axis between minus 5 and 5, which is what they want you to think, right? They want you to picture another graph like this that's just symmetrical between minus 5 and 5, and so the areas is the same. But that doesn't have to be the case. And again, we're thinking counterexamples here. What about this graph? This wild graph that, let's just pretend this is the point minus 5, and this is 5, and this area here is equal to this area here, which it looks like it roughly might be. Of course, that means that this condition doesn't have to be true, because this graph is clearly not symmetrical in the y-axis. This condition is definitely makes this true, right? Because if you just make the graph just a straight line across, then the integral between minus 5 and 5 are equal. It's symmetrical. But it doesn't have to be true because of this example here. So we can cross that out. And this one here, I'm sure again, if you drew a graph that if you rotated it or reflected it in the x-axis and then the y-axis or vice versa, I'm sure that would probably make this true if you drew a graph that followed that. But again, it's not necessary because this graph does this, and I'm pretty sure if you reflect this in the y-axis and then the x, you don't end up with the original graph. So that's also not true, and we have none of them. So not only can we find numerical counterexamples like in the first few examples, but we can also do it graphically. And as soon as we see language like which must be true, what's necessary, just look for counterexamples. If you can't find any, then think it through a little bit more. Maybe you're missing something. Maybe the maths just means it has to be true. Or if you can't think that through, just guess, because your counterexamples will have reduced the options available, and your guess will have a more likely chance of being right. Anyway, thank you so much for watching. I think that's the end. Yep, it is. Cool. Did a lot of examples there, but whatever. I'll see you next time.